All right, guys, we're going to move on today and talk about logarithmic functions. And very important, essential question here, which is how do we solve equations when the variable is in the exponent? That's the big idea on logarithms, is that when we have a variable in the exponent, there's no other way to isolate that variable other than using logarithms. So that's really why we have them. Now, we're going to first talk here about logarithmic form, and what it really is a different form of an exponential equation. So we've just handled exponential equations, and so now it makes sense that the next thing we do is logarithmic equations, since it's just a different form of that. So our exponential equation here, I wrote it as, and these could be whatever you want them to be. So I have a base of a to the power of y equals x. So you can see that is an equation. We got our equal sign in there. And then if we switch that into the logarithmic form, it is, we write the word log, and then there's a subscript base, which is the same as the base over here. And then what's in there is x, so that kind of switches from being away from the a to being close to it. And then the y is all by itself. So we're going to practice that a lot today as we move forward. So next up, though, a couple more pieces of vocab here. So a common logarithm. And this is actually, we said that there's always a base of a logarithm. That's that a back here. But there is actually sometimes when the base is not written. And if the base is not written, it is assumed that it is a common logarithm. And that's going to be of base 10. So it's that assumed base 10 if the base is not written. And then lastly here, we're going to have something kind of similar but a little bit different, and this is called the natural logarithm. And so a natural logarithm is denoted as ln. And so I think that means like log natural, or it probably comes from like the Latin. So I don't know how you say that in Latin, but loge natural, and that's why it's ln instead of nl. In English, we say the adjective first, but that's what it is, ln. That is a log, and so that's going to be a log with base e. So you could kind of think of it like log base e is the same as ln. We just write ln for short. E is a really important kind of a number when it comes to exponential equations, which we talked about last section. And so it kind of makes sense that since it's so important for exponential equations, it's also very important for logarithmic equations. Okay, so now we're going to work on switching from one form to the other. So we need to know how to do both, and so I'm just going to kind of set it up here. So we're going to start off here. We'll start off with an exponential equation, and so I'll kind of color code this. So let's go exponential equation. And so on an exponential equation, we always have a base, and this time I'm going to call the base b, just so it'll be easy to, because I'm literally saying that b stands for base. And remember, a base always has an exponent, so let's make this one an exponent of x. It doesn't matter, remember, what these variables are, right? They could be variables, they could be numbers. We'll always have an equal sign, and then it's going to equal something else. And so I'm going to let it equal, let's say, y. Okay, and so when we're going to switch that to the logarithmic form, so let's switch this to log form, we're always going to write the word log. That's kind of the essential part of a logarithmic equation, is that we literally write the word log. Obviously, the word log is not in the exponential equation because it's not a logarithmic equation. Now, every log has a base. Like we said, it's a little subscript. And so in this case, since the base is b, the base is going to be b. And so what I always say is the base is the base. And so both of these forms have a base. Now, in the exponential form, it's a base is kind of written as a normal number, whereas in the logarithmic form, the base is written as subscript. But the base of the exponent becomes the base of the log. And then the next thing I say is it gets a new partner. So b is with x right now, but let's just say it's kind of sick of x. It doesn't want to be with x anymore. And so it's going to get a new partner, and let's see who's available to be with the base. Well, y is over here. I can say y is single, so they're going to get together. And so now the y goes inside the log, like so. It's written as a normal letter or number. And then, so what happens to the x? Well, now the x, since it broke up with the base, is all over here by itself. So that as you can see, goes back to answering our essential question here. How do we solve equations where the variable is in the exponent? So this variable that was in the exponent up here is now isolated over there. It's all by itself on its own side of the equal sign. So that's the crucial aspect of the log. Now remember that we can now, because we do need to know how to switch from exponential to log, but we also need to know how to switch to log from log to exponential. So if we pretended that that first step was not there, and we had this exponential form, and we want to switch it into log, so remember, if we're going to switch the, when we're going from log to exponential, we don't have the word log anymore. So we're just going to start off with a base, and the base of the exponent comes from the base of the log. So that just comes right there. Now that we're switching this way, it still gets a new partner. So that's my trick for these, is the base and it gets a new partner. So now B is kind of sick of Y. And so what happens when it's sick of Y? Well, it wants to be with someone new. And sometimes if you can't find anybody new, you just get back with your X. That's a little exponential logarithmic joke for you right there. And so what happens to Y? Well, now Y is back to being on its own. So those two kind of switch off being alone versus being with the base. The base always has a partner, but it switches every time you switch. All right, so we're going to start off here just switching from one form to the other. So we're not trying to solve any of these. So they should already be true equations. You can see here 10 to the third power does equal 1,000. That's true. 2 to the fifth power does equal 32. Anything to the 0 power is definitely 1. And remember, a -1 power drops something down to the denominator. So that's not in question here. What we're trying to do is switch it into the logarithmic form. So remember that the base of the exponent becomes the base of the log. So first of all, if I'm going to switch to log form, I'm going to write the word log. It needs a base, and so the base of the exponent becomes the base of the log, and that's 10. It wants a new partner, so that's 1,000. And so that means what was in the exponent with the base is now isolated over here. Now I was about to box that up, but some of you may have been thinking, hey, Mr. Berry, that's a base 10. And we said earlier that if it is a base 10, we can actually write it without a base. And so if it is base 10, we're just going to write it as log 1,000 equals 3. When we don't write a base, it is, once again, assumed that it is a base 10. Okay, next up here, number 2. So this one, we got a base here of 2, so I'm going to write it as a log base 2. And then inside the log is going to be a 32. And then what was with the 2, what was with the base, is now isolated, and so that's the 5 over there. So that's our answer for number 2. All right, number 3, same idea here. So we're going to do log, and then the base of the exponent is going to become the base of the log, but it's going to be with a new partner. It doesn't want to be with 0 anymore. Now it's going to be with 1, and then that's going to equal 0. All right, so you can pause here if you'd like and go ahead and try out number 4, and I'll go over the answer in a second. All right, and so if you did number 4, your answer should say log with a base of 8, and then the new partner is 1 over 8, so that's going to be inside the log, and then that equals -1. All right, so now we're going to go the other direction with this. And so now it's given to us in the logarithmic form, and so we're going to switch it to the exponential form. And so for the first one here, so when we switch out of log form, we should not have the word log anymore. That's gone. So now what we should have is an exponential. We should have a base with an exponent. So remember, the base is the base. So our base is going to be 3. So I'm going to draw a regular size 3. Its exponent is going to be the new partner 2, and then the old partner 9 is going to be on all by itself. So once again, we know that 3 squared is 9, but that's kind of not the point of this. The point is that we switched it from the log form. All right, next one, number 6 here. If you want to pause and go ahead, you can do that. All right, and so number 6, there's no base written, and so whenever there's no base written, it is always assumed that it is a base 10. That was the common logarithm that we talked about at the beginning. And so when I switch this to the exponential form, the base of my exponent is going to be 10. And then the new partner is going to be -1. And then that is going to equal 0.1. Now, once again, that is certainly true because 10 to the negative 1 power is 1 over 10, and so that equals 0.1. All right, now we got number 7. Once again, if you want to pause it and go ahead, you can do that. And so number 7, we have our base here is written as an 8, so we're going to go 8. The new partner is going to be to the power of 1/3, and then that's going to equal the old partner, which is 2. And this is definitely true, remember, because the 1/3 power really means the cube root, so the cube root would turn an 8 into a 2. All right, lastly here, a little bit of a tricky one, but we do need to know how to do this one as well. So we have an ln here. So ln is, again, it's a log with a base not written, but because it's an ln, a natural log, the natural log is always base e. So a little different here, and you have to know the difference here. The log with no base written is 10. ln with no base written is e. You're never going to have an ln with a base written because ln is always a base e. So if you'd like to write the little base e in there, that might be helpful. So now it's the same idea. Remember that L in ln does stand for log. So we're just going to treat this like any other log. We're going to switch it to exponential form. The base of the exponent is going to be e to the power of 0. And then that's going to equal 1. So e, the new exponent, is 0, and then that's going to equal to a 1. That is certainly true. E to the 0 does equal 1. Remember, anything to the 0 is 1, and e really is just a number. It's a very special number, like 2.71828 onward like that. But it is a number, so it does act like all other numbers when it comes to something like a 0 power. All right, next step here, we are going to evaluate these. And so we're going to figure out what is log base 6 of 36 without a calculator. You can do these with a calculator, and it's a lot easier. We'll learn how to do that later. But for now, we're going to do it without a calculator. So how we do that is we always want to switch from whatever form you're in. So in order to switch, we need it to equal something. So I'm just going to let it equal x, since x is going to be our answer to this question. And so then we're going to do our exponential switch. So the base here is 6. So I'll switch it 6 to the power of. The new partner is going to be x equals 36. And so then you just have to know, well, 6 to what power gives you 36? Remember, we're talking exponents here. So that's going to be the second power. 6 squared gives you 36. All right, next up here, number 9. So we're going to let this equal x as well. All right, and so remember this one, there's no base written, so we're going to say it's a base 10. So it's going to say 10, and then the new partner is going to be x in the exponent, and that equals 10. So 10 to what power gives you 10? Well, I think that's pretty clear that that's going to be a 1. Number 10 here, we'll once again let that equal x, and then we're going to do our switch. So the base is 5 to the power of x equals, and then this whole thing, 5 to the 4th power, was inside the log. So since that whole thing was inside the log, now that whole thing is isolated all by itself. And so from there, you could do 5 to the 4th power. I would not even do that because I think right away we can see that x must be 4 in order to balance that equation. All right, next up here, number 11, once again, set that equal to x. And so we got 49 equals, oh no, not 49 equals, excuse me, 49 to the power of the new partner. So the base is 49, base is the base, it gets a new partner, to the power of x equals 7. Now this one right here, remember we're talking about exponents here. So when I think about an exponent that turns into, that turns 49 to 7, I'm really thinking of the square root. And so for the square root, remember the square root can be written as the fractional exponent 1/2. So remember that 49 to the 1/2 power is really just equal to the square root of 49. Very important on this section that we remember our fractional exponents, meaning roots. All right, number 11 gets a little tougher still. And so let's check that one out. So we're going to set that equal to x. And we're going to say 8 to the power of x equals 4. Now, some people can do this one in your head. The answer is not 1/2. Remember, 1/2 is the square root. So it's not like we're multiplying it by 1/2. We have to think of an exponent. So The way I would recommend doing this is making these now the same base. So we know we can write these both as a base of 2. So I would write this one as 2 squared. And then I would write this one as 2 to the third. But then the x is still over here. So I've just kind of changed the inside to call it 2 to the third, since that is 8. And then we know with our properties of exponents that we can just call this 2 to the 3x. We're allowed to multiply those because it's a base with 2 exponents. And so now that I have it just the same base equals the same base, I can just set the exponents equal to each other. So I can say 3x equals 2, and then divide by 3, and I get my x value at 2 over 3. So that's how you do those ones when it's when you can't turn that into the other one. Just make them both have the same base. All right, next up, number 12. So this one I'll set it equal to x. And then we'll say 3 is our base to the power of x equals 1 over 27. Now, whenever we create a fraction like this, this tells me that the exponent is going to be a negative. And so I already know that x is going to be negative something. And then I just think, well, what power turns 3 into 27? And that one I can do in my head as negative 3. So the 3 turns it into a 27, the third power, and then the negative drops it down to the bottom. All right, next up here, number 13. So we'll do that again, set this equal to x. And so if you want to pause this one's going to go kind of similar to number 11. It is a tricky one, so if you want to pause and try this out just like we did number 11, you can go ahead and do that. And now we'll go over the answer. All right, so we're going to go 9 to the power of x equals 27. I don't know how I can turn 9 into a 27 using an exponent. It's not a 3 because the 3 would be 9 to the third power. That would be way bigger than that. So I'm going to turn these both into a base 3. So this one's going to be 3 squared to the power of x. The x was on that side. This one's going to be 3 to the third. And so it'll be 3 to the 2x equals 3 to the third. And so now I have the bases the same. I can just say 2x equals 3, divide the 2 over, and we can say x equals 3 over 2. All right, we're going to pause it there for today. We'll pick up, finish the rest of this section at a later time, and I'll see you guys later. Bye.